Everyone, my name is Chantal and my project is called Assessing the Viability of an Arduino-based Environmental Sensor for Gathering Climate Data. As the name suggests, my project revolves around the idea of an Arduino-based environmental sensor. This project was inspired by the several $1,000 Nakano, where the ultimate goal was to get the Arduino-based version functioning and deployed. Hopefully, with the creation of the Arduino-based environmental sensor, people can have multiple weather stations that are cheaper to make and thus allow a better understanding of the environment around them. The phase of the project 1 consists of setting everything up and learning about how the sensor works, particularly the CCS811, a temperature and relative humidity and pressure sensor, where I focus on the dependability of its temperature readings due to the limited time and the equipment available to me. This means programming the sensor, wiring everything, and ensuring that it works as intended. While I was new to coding, the majority of the problems that I had with the code were resolved relatively quickly with the assistance of the peer mentors, and the same can be said about the assembly of the sensor. During this stage, many intricacies of the components were noted, such as the specific order in which the sensor and the microSD card needs to be removed in order to preserve the recorded data. Specifically, anything done to the microSD card, removing or inserting, needs to be done before or after the power is given to the system. If done while the system is on, no data from the sensor will be saved onto the microSD card. Some other things that people should be aware of is the sensors, the CCS811 and the BME280, have different modes that can be set. This can have possible implications in the data collected by increasing reading accuracy, but at the cost of consuming more power and vice versa. Also, keep in mind that the sensor is intended for indoor use only. This poses an interesting implication where the sensor's manual mention averages and baselines involving calibrations. I was unsure of how these baselines played into the role of correcting for the directly measured data, temperature, relative humidity, and pressure, since it wasn't specified. I further noted that the manual ensured that the user had no ability in altering the calibrations for whatever reason. But because of my inability to produce data that could be verified, the cognicy of my sensor, it is irresolute whether the aspect of the sensor will pose any issues in the future. The main issues of this project arose concerning the abilities of the open log, a piece of hardware used to record data onto the microSD card, and its inability to record data independently from the serial monitor, a piece of software that tells the sensor to start recording. This independent recording was integral for the sensor's ability to be deployed out on the field, since it would be impractical to maintain a laptop or computer along with the sensor. It was brought up with the possibility of writing code to trick the open log, thinking that there was a serial monitor open in order to circumvent the problem. However, with the level of programming experience that was needed and the time restrictions, it was determined that a better course of action was to implement a new open log from a different company, Adafruit. Because of the new hardware, additional parts needed to be assembled and wired, as well as some changes to the code were made. In the end, I was able to get the sensor automatically recording the data without the use of the serial monitor. Though this issue was solved, the sensor's practical ability to be deployed onto the field was put into question as the jarring of wires were easily broke the connections. Since the sensor would need to be placed on the field with no live monitoring, it would be risky to place the sensor not knowing if it was functioning. And with the consideration to the specific order in which power must be cut, the unplugging of wires, even when placed back, can null any record data. It becomes even more imperative that none of these complications occur because of the required time it takes for the sensor to give access, where it needs to run 20 minutes. While as a lab unit, I would only need to place the sensor out on the field for an hour or so, the impracticality and the risks associated with deploying the sensor for weeks on end quickly diminish in returns. I determined that soldering the wires would likely mitigate the problem, but limiting time and resources led to the halt in implementing the solution. While these were my issues with the hardware and recording of the data, the sensor posed a whole new set of issues and problems. The sensor that I used for this project was a 2-in-1 sensor, the CCS811, a temperature, pressure, and relative humidity sensor, and the BME280, a CO2 and TVOC or total volatile organic compound sensor. This means that both sensors are located on a single piece of hardware, where the BME280 has the possibility of heating up and altering the CCS811's readings. My goal with this sensor was to compare the data collected to that of the CAMBA or onset sensors, the expensive sensors, to get an idea of how accurate the Arduino-based sensor is and whether or not it is a viable option with reasonable levels of error. This particular sensor as a whole was advertised to be able to give the user CO2 and TVOC readings as well as altitude readings. Implementing the CO2 and TVOC sensor would have been a first among Allah, allowing a new aspect of the mountain to be monitored and evaluated. However, upon further research, it became apparent that these values were not directly measured and were calculated, rendering the validity of these values to be questionable. Uncertainty persisted when the company, though stated that these values were calculated, did not elaborate on the particular calculations that was done to get these values. It can be assumed that somehow temperature, pressure, and/or humidity play factors towards these calculations, but with no other third-party CO2 or TVOC monitors available to me, I was unable to determine the legitimacy of the values. If I was able to compare it regardless of how these values were calculated, we could at least determine if we can trust the numbers that came from the sensor. However, since this was not the case, and thus I decided to focus on aspects that I could compare, mainly that of temperature. With more readily available third-party measuring tools, temperature was the easiest to verify, primarily that of analog thermometers and the CAMBA and onset sensors. Briefly, it was considered to place the sensor in an oven on its lowest settings, 170 degrees, but even that would have been too high and would have broke the sensor. A third-party measuring tool, the analog thermometer, posed its own set of challenges. That being the only thermometer available to me was an old cooking thermometer that was intended for the use in scalding liquids. This means intervals between the markings were fairly large, 5 degrees per tick mark, and its reliability as an air thermometer is questionable. Not to mention that it seems to be an alcohol thermometer, which is less accurate than a mercury thermometer. Upon testing the possibility of it being even remotely accurate, I tried it on myself with a normal body temperature of 98 degrees Fahrenheit. It gave a bodily temperature of roughly 89 degrees Fahrenheit, where I was not in any state or form suffering from hypothermia. These were unpromising readings that I decided to omit from comparing it to my sensor. Issues rose quickly with the access to the Campbell sensors because of its location on Mount Allah, where at the time limited range is given to vehicles traveling up the mountain due to both area restrictions and road work being done. While hiking proved to be a possibility, the amount of effort required to hike the highest mountain on Oahu would not be considered a practical option. A less tiresome choice became that of visiting the onset sensors at HCC, Honolulu Community College. And with that, more walls were presented with further restrictions to the campus due to the COVID-19 pandemic, where students were restricted from entering the campus grounds without explicit permissions granted beforehand. This resulted in my ability of visiting the campus for only one set of readings for roughly 5 minutes of data that could be collected and compared. Upon further consideration, the data collected at that time would be considered non-viable due to the poor test design, where the recommendation of a 5-foot height of the sensor was not followed. Specifically, the CCS811 was roughly 10 degrees higher than the onset sensors. What was promising was a general decrease of the temperatures that both sensors noted during the same time. Granted, it wasn't at all proportional, and the 10 degrees drop from the Arduino base sensor is huge compared to the roughly 0.5 degree drop, the HOBO graph. Hopefully in the future, the runs that are conducted, the correction for the test design will amend for the differences. Ultimately, I was unable to produce any significant values to compare the validity of my sensor's data, and thus I am unable to make any conclusions about its accuracy. Further testing will need to be continued in order to make any conclusions. Also, lab units, what my sensor was practical for lab use only. It's fragile and finicky, and with other with the order, in which you need to unplug the power source and the micro SD card, not to mention how easily jarred the wires can become with simple movements. You can also learn from my mistake and understand that test procedures are essential, and if not followed exactly, can lead to very skewed data points. Not to mention the classic, don't always believe what you're told, especially by companies. And while they don't outright lie, perceptions and assumptions can be toyed with and shifted for the company's favor to implore you to buy their product. In future work, since my readings with the temperature data was considered void, I would like to see the assessment of all directly measured data types, temperature, pressure, and relative humidity, as well as calculated CO2 and TVOC values, being compared to already established and reliable counterpart sensors. And if all goes well, create a field unit that is able to withstand high humidity, mild abuse, and direct radiation from the sun. As a final note, I'd like to thank a few people who have helped me through the project and guided me through all the bumps and roadblocks. Mevan Ranasinghe, Mia Fong, Leo Tanaka, Anthony Lopez, Catherine Bronston, Dr. John DeLay, and Dr. Shidong Khan. Thank you so much for your support, and thank you for listening to my presentation.